Hello, this is the Tepid Coder. In this video, I want to conclude the C++ standard list implementation. So, one thing I want to change here, if you see we have a count, a back, and a front pointer. So, if I were to copy this list right now using the default copy constructor, it's just going to copy where these pointers point, and then in the structure of both the copy and the original class, when they destruct, it's going to try to free each one of these elements using the delete operator. So that's actually a problem. When the second class destructs, it's going to have undefined behavior, which is probably going to cause a second fault. So we should fix that by implementing our own custom copy constructors. And I'm going to implement all of them: the copy constructor, the copy assignment operator overload, the copy assignment operator overload, the move assignment operator overload, and the move constructor. So let's do that. List, it's going to be const list reference. Okay, that's our copy constructor. This will be the move constructor. We'll do operator equals, and we'll say list, like that, be the move. Yeah, there we go. Let's move assignment operator overload, and we're going to do the copy assignment operator overload. Yeah. Okay, let's implement those. I think I'm also going to want to do merge front. It's going to be a no accept, void merge back, void no accept. I'm also going to want to do something like, let's say t front, void no accept, t back, void no accept. Okay, we'll implement all those. And that should pretty much finish up everything I wanted to do with the class. So template type name t. Okay, let's take these. Implement those as well. Oops. Okay, so for the copy constructor, I basically just need to say the count starts out as 0. So mst count will start out at 0. Okay, and I'm going to say for can be list to some type, which by the way I need to say where this comes from. It comes from this class specialized for type t. And it is the constructor, okay. It's copying from list also of type t. Good. So that's going to be iterator. In fact, I'll say const iterator, because I'm making a copy. Equals going to be old.c begin. Okay. I'm going to say cit does not equal old.c end. I'm going to say cit plus plus. Okay, and I'm just going to say for this class, push, let's say front. It can be pushback, doesn't really matter. I'll say pushback actually. That way it stays the same ordering. I'll just dereference cit to get the underlying t inside of it. Okay, that looks good. So the count starts at 0, and it's going to increment every time I push back, and it's going to push back for every node inside that list to make a copy of it. That way when this list right here that we're constructing with the copy constructor, gets destructed, it's going to free its own copy of this list instead of freeing the same node pointers in memory. Like they're both going to have like their own node type t pointer for each node. Okay. And now for the move constructor, it's even easier. I'm just going to say that m front equals old m front, m back equals old m back, m st count equals old dot m st count. And I could say old dot m front equals 0, or I'll say null pointer. I'll make it more idiomatic. Old dot m back equals null pointer. Old dot m st count equals 0. Okay, I can basically just steal that and use that for the move assignment operator overload. Okay, and I also need to return this. So So right now this refers to list type T pointer. So if I dereference that, I get list and, which is just like list. So that's what I'm doing there. Now I have to do the same thing here. So return this. This comes from list. For selector type T. This is also list T, old. This comes from list type T. This is also list type T. Yeah. Okay. Return a list type T. So this is the copy assignment operator overload. In this one, I'm just going to do the same thing as the copy constructor, essentially. So let's do that. But before, in this case, I need to say mst count equals 0. So if this already has contents, I need to make it so the contents get wiped out. It also means I need to do this clear before. And that clear right here is going to set the count to 0 anyway, so I don't need to do that. So if I look at list t clear, here it is. Count becomes 0. See, that's good. Let's do clear. There it is. Yeah. Same thing here. I'm going to do clear. Okay. So when I move construct, yeah, I'm just assigning all of our stuff to the same thing as their stuff, and then I'm basically invalidating their pointers, which is like I called clear on that class, even though I didn't. That way, when this one destructs, it has nothing to free, because we stole all of its contents. Okay, and this one copies, so we have our own version of the contents, that's fine. This one also copies with assignment, and we have our own version of it. If we had anything previously, it gets cleared out. We return this for training. Okay, and then the move assignment operator overload gets cleared out, and then we steal its contents and null it all out, so when it destructs, it doesn't try to free us the memory we do. Okay, they return this for training. That looks pretty good. So I'll do merge front now. If I'm merging in the front, what I need to do is I need to make it so, first of all, we can't merge from the same list. So let's do list T is where this comes from. I'm just going to take a regular reference. We're going to steal the contents of this list. So if place the list exists in memory is equal to place this class instance exists in memory, then do nothing. We can't merge ourselves into the back of ourselves. That would be kind of weird. So I'm going to say our back element equals this list's, our back's next element points to their list's first element, and their list's first element points backwards to our last element. Okay, so then I need to say our back in back now equals their list back. Okay, and after that I can just invalidate their list. So the list m back equals null pointer, list m front equals null pointer, list dot mst count equals 0. That looks pretty good. Over here I'm kind of doing something similar. If the list is equal to this, they point to the same address, our class and their class. They're the same place in memory, so it is the same class instance. And we just bail. So I'm going to say now in this case, m front lb prev equals their back. So list m back. Okay, and then list m back lp next equals m front. So their back points to our front. Yeah, I got these backwards. So I'm merging this one in the front. Merging this one in the back. Yeah. Anyway. Yeah, okay, so after that, m front equals list m front. So we put their list in front of our list, so our front points to their front now. And our back stays the same. In this case, our back becomes their back, and our front stays the same, because their list comes after ours. So our back points to their front points to our back, and our back now points to that back. Okay. And we invalidate them because we're stealing their pointers. Okay, and this one, if it's not the same class instance, then we're going to say our front's previous points to their back. So we're at the end of their list now, and then their back also points to our front, so it connects. And then their front is now our front. Okay, now we need to invalidate all their stuff. So mFront equals null pointer. List dot mBack equals null pointer. List dot mst count equals 0. Okay, that's a lot there. Two more things though. So now we're gonna say return. It's gonna be mFront t data, and here it's gonna be return mBack t data. That's a lot of stuff to test. Let's go into our main function. Let's make some test cases. So first of all, I'm going to say I have list type int. Let's call it list3. Okay, if I say list3, let's do this, equals list, right? Pretty sure I have a list2 and list3. Yeah, list2 is dates. List1 should be just a bunch of integers, right? What am I putting in there? Right here, yeah. So 1, 0, 2, 3, all this garbage. Pop the front, pop the back. So we're deleting the 1, we're deleting the 4, so we have 1, 0, 1, 2, 3. And then what's happening after that? We're erasing 0. Okay. Oh, that's something else too. So if I go to my list t erase function, I actually changed it kind of how I showed in the comments in the video. So I said that if I make it a constant reference, you can actually have a method, so like class method, which takes a const t reference. A const t reference, you can actually just pass a t. It doesn't have to be t and. So like if I make a tt like this, and I say, you know, class method t like that, and I let it pass a t and, that would satisfy this. But if I just pass something like, I don't know, some type t, let's say t is an int, right? Like int 5 equals 5, right? Equals 5. Whatever. If I just pass a 5, that's a temporary value, right? But that'll still work if it's const. So how I implemented that here is I made it so that this takes a const reference, and then I had to make it so that the actual node that I get from my iterator returns a well, I'll show it. So class iterator. Where's my get node here? So it returns as const. Otherwise, that taking a const t, right? That was class method const t and. That means it actually has to be a const method, right? Otherwise, I couldn't return this. So I'm returning a const node pointer in const qualified method. So I'm doing that, but then I kind of have to lie a little bit. So list t erase. I'm doing const cast, which removes the const qualification, because I'm not necessarily using this in order to be able to manipulate the value so much. I just want the actual underlying node here, and I want to delete it. I don't really want to modify the value at the node, so it is kind of like the t is being treated as const. I'm not manipulating the t. It's just that the node containing the t is being deleted. So it's a little kind of weird to look at and think about, but either way, I did make it so I can delete based on, like, you know, list begin, as you can see in the main function. If I do list erase, you can see I just did list begin here instead of having to do this, define a temporary and then pass it. So I just did that to make it easy. So anyway, we had -1 gets deleted, the 4 gets deleted, then I deleted the 0 explicitly, so I have 1, 2, and 3 left. So I'm going to say this equals list, so it equals 1, 2, 3. Okay, I'm going to do list for each. I'm going to say takes a const int reference, call it I, returns bool. Okay, and then I'm going to say return true, so it goes through every element in the list. Standard cout line. And we're going to do something like list3 value I. Okay, I'm gonna need a bunch of those. So that's with the copy constructor. Next one is gonna be list4. Also type int. I'm gonna say list4. Oops, what am I doing? List4. And then I'm gonna say list4 equals list3. This is calling the copy assignment operator overload. So it's operator equals const t, or well, I shouldn't say const t, const list t. And over here, this is going to be list t, const list t, and yeah. I just want to make it as explicit as possible so I don't confuse anybody. Anyway, cool. Then we have our move constructor and move assignment. So I'm going to say list int list 5 equals standard move from, I'll do list 3, I want to do list int list 6 equals, or sorry, list 6, and I'll say list 6 equals standard move from, how about list 5? Okay. So now for each of these, what I want to do is actually print out what happened. So there's another copy. I'll even say what I'm doing. So standard cout, copying list into list 3. I'll say copy constructor. Cool, and then we print it out. And we'll say copying list 3 into list 4. Copy assignment operator overload. Okay. Cool, then we print it out and standard cout. Moving list 3 into list 5. Move constructor. Okay, then we should print that out. 5 right here. This is 4. I guess this will be 6 when I get to it. Okay. Standard cout. Moving from list 5 into list 6. Move assignment operator overload. Okay. Yeah. So now some things I need to do here. This list 3 value here, this is list 4 value I'm printing out. 4, okay, and this should be 5, and this should be 6. When I move, it also means that the other list count should change because I stole its members. So I'm going to say moved from, what is it, list 3? So list 3 dot count. Okay, we're going to say it is list 3 dot count. Cool. I'll do the same thing down here because I'm moving from list 5 into list 6, right? Yeah. Okay. So standard cout list 5 count. Okay. It's going to be list 5 dot count. Yeah. What else did I make? Oh, I know what I did. I did standard cout. Let's do list 3. Actually, I deleted list 3, didn't I? It was a copy of list. That's good. But then I moved it, didn't I? I copied it into list 4. Then I moved from list 3 into list 5. So that doesn't exist anymore. Yeah, it'll be empty. So I need to do like list 5, but list 5 went to list 6. So I'll do list 6 then. Okay. Dot back. There we go. So then list 6 dot back. Standard inline. I'll do the same thing with the front. So front. Front. Oh dear. Anything else I made recently? I think that's probably enough changes. Let's test that for now. So I'm going to do g++ test.cpp dash out test. I want to do standards equals c++ 20. Okay, so 230 missing template argument. 230. Right, so I need to do, this comes from this type T, this T, like that. Okay, let's try that. Okay, T43, no declaration matches that. To T43, that's right, I did change it. T43. Merge back, merge front. It's right here, same thing, list T. It's going to take a list type T, reference list. Okay, let's actually find out where I define that. Right here. So list. Okay, and over here, list. Come on, list. Okay, 270. Front was not declared in the scope. 270. Yep, because that comes from the class. It's list type T. Okay, list type T. Alright, try and run it now. Cool. So what do we have? Copying list into list 3. I have 1, 2, 3 from list. That looks right, because 1, 2, 3 is left. Yep. Okay, then we're copying list 3 to list 4. 1, 2, 3. That was the copy assignment. We're moving list 3 into list 5 with the move constructor. The count becomes 0 for list 3 because we moved from it. Remember that? And it has 1, 2, 3 now. We're moving from list 5 into list 6. List 5 count becomes 0 because we're moving from it. So we went from 3 to 5 to 6. It has 1, 2, 3. The front is 1. The back is 3. So now here's something I want to do. If I go back into my main function, list 1, just regular list, should still have contents in it. So I do, I'm going to do list 6 dot push front. I'm going to give it a negative 1, or make it a big number, negative 99. I'm going to say list 6 dot merge front. I'm going to merge list into it. So what I should have here is list 6. It's going to be 1, 2, 3. Okay, and then it's going to be list 6. It's going to be negative 99, 1.2.3. Okay, and over here it's going to be list 6, colon, 1, 2, 3, negative 99, 1, 2, 3. Right? Because I'm pushing this list before us. So let's see if that works. Okay, I didn't actually print it out again. That was a bit of a blunder. Let's do I'll do list int const iterator. Oops, iterator cit equals. We'll do list 6 dot cn cit not equals list 6 dot cn. Okay, cit plus plus. Okay, we'll do standard cout, list 6, value. We'll let this in quotes so I can differentiate a little bit better. Okay, and CIT. Okay, there we go. Dereferencing that. Okay, so we have 1, 2, 3, negative 99, 1, 2, 3. Because it had 1, 2, 3, we put negative 99 before it, and then we merge the front. Well, that's kind of interesting. Yeah, that's right. Okay, 1, 2, 3, there's negative 99, 1, 2, 3, and then we stuck this in front, which is 1, 2, 3, negative 99, 1, 2, 3. But if I merge back now, what I should get instead is going to be list 6. Should be negative 99, 1, 2, 3, and then it's going to be 1, 2, 3 again. Right? Right. So let's try that real quick. List 6 dot merge back list. So we're sticking their list at the end of ours. Okay, so I messed that up. Okay, 248. 248. Really? In front. A little misspelling there. Okay. And what do we get? We get negative 99, 1, 2, 3, and then 1, 2, 3, just like we thought. Alright, there's one more little thing I want to do to make this a little bit faster. I mentioned this in, I think, the first video about this. And that is, instead of making an iterator to compare with this operator overload, and then comparing it, what I could do instead is something like be done, or bool done rather. I could say it's void, it is const, no except. And all it's going to do is simply say return mNode equals null pointer. So if our node in this iterator is currently pointing to nothing, then it's done. If that's not true, then it's not done. That's all that's doing. That's a bit faster than having to create a new iterator object that points to 0 and then compare it with the operator overload with another iterator. So let's look at const iterator now. Oops, yeah, class const iterator. Okay, put that here. Domain, not the same, or whatever is typed. Okay. Okay, and instead of saying not equals this, I'm just going to say cit dot done. So not done. And keep looping. And there we go, works just the same. And that should be slightly faster, because it's not creating a new object every time. In this case, it was actually calling list end, right? Every time it calls list t the end, we're getting a list type t const iterator, which is constructed with 0 or null pointer. Okay, and then we're comparing that with list t operator. Oh, wait, list t const iterator operator not equals with the thing I just constructed, this right here. So let's say I have something like list t const iterator it equals, you know, whatever dot cend, and then we're comparing it right here. So it's constructing a class object, it's calling a function to compare it, it's doing all that instead of just calling this function. And I could be even faster than this if I just had a variable called like be done, and if it reaches 0, I would just test it to be done. Or I could even just expose the underlying node t pointer, whatever this is. I could just expose p with an accessor and see if it's done. Either way, it's still kind of calling a function. Or if I could just make it so that that node p is just exposed as a public member, that would also work. But then you're kind of relying on the person not to mess with that variable outside of the methods exposed by the class, which is bad for encapsulation. So I think we should at least be willing to make this concession. It's slightly faster than constructing an object and testing it and throwing it away immediately. I mean, the destructor is pretty trivial for this, but I don't know. I like having this option. So I'm trying to think. Is there anything else I want to talk about? How about list t erase? So I mentioned this in the comments of my previous video, like actual text over the screen in post-production. If I was erasing a node and there's only one node in the list, and I had an else clause here, this would happen, but this should also happen because there's only one element in the list. So I'd be invalidating the front pointer where it references, but I wouldn't be invalidating where the back pointer references, even though I should because it's the only element. So both the front and the back are pointing to the same thing right now. In any event, I think this is a pretty good implementation at this point. I've covered the vast majority of what a standard list lets you do. Anyway, if you guys got something out of this, give it a thumbs up, consider subscribing for more content like this, and if you have any suggestions for more things I should probably do with this class to make it more complete and maybe fix any bugs or something, because like, I did need to add this before, and I did now. I'd like to hear it. If you have any criticisms, I'd like to hear that too, things I can improve upon. If you have any other thoughts, feel free to post those too. I like reading them. Anyway, I think I'll catch you guys in the next one. Have a good day.